different properties of different properties of Fourier transform. We start with linearity. linearity Linearity property is ax1t plus bx2t is denoted by a x omega plus b x2 omega. Linearity property is combination of two rules, superposition and homogeneity. Example for linearity property is x e power minus a mod t. We already done. Expansion of this term is at u of minus t. As per linearity property, we have to add these two transform and result will be addition of these two. 2a upon a square plus omega square. Final Fourier transform of this pattern is, by linearity property we can conclude Fourier transform of this pattern is come from this linearity property. Individual term added and result will be addition of these two. From subtraction we can e power minus at ut minus e power at u of minus t. From subtraction we can also form another Fourier transform of signum function limit a tends to 0 xt ut u of minus t. Fourier transform is 2 upon j omega. We already discussed before. Now move further to second property, time scaling property. Time shifting property. If we signal is time shift by t naught, what is the effect of time shifting is with the time shifting magnitude spectra is not change. Only phase spectra modified. Spectra is modified by this amount. Linear phase is added to the system by time shifting property. Time shifting property can be proved through change of variable. We can simply put, instead of xt we can put xt minus t naught. We can simply put this value and result will be modified by this amount. So time shifting property can be proved by change of variable. Time shifting shift in the time domain will produce linear phase shift in frequency domain. Spectrum is linearly phase shift. Application of time shifting property means distortion-less transmission. For distortion-less transmission, magnitude spectra is unchanged. Magnitude spectra not change. Phase spectra is linearly varying. Spectra is linearly varying. Third one is frequency shifting. Frequency shifting. Now we apply shift in the frequency. XT. It produce shift in the range of frequency by some amount. Frequency shifting property is dual of time shifting property. Dual of time shifting property. Later we discuss the what is duality. Dual of time shifting property. Frequency shifting property also known as modulation property. Modulation property. This also can be proved through change of variable idea. We can prove through change of variable. Instead of using xt, we use this term, then result will be modified by this amount. We can prove. Let's see. Xt dt xt e power minus j t omega minus omega naught dt. Omega is replaced by omega minus omega naught. This term is synonym to this term, but difference is omega is replaced by this term. We can rewrite this term in this way. So with the frequency, with multiplication with exponential component, frequency is shifted by some amount. It is known as modulation property. Next property is scaling property, time scaling property. Fourth one is time scaling property. Time scaling property. At equals to mod of a x omega upon a. It is known as time scaling property. This is also proved through change of variable. If a is greater than 1, time compression. If a is less than 1, time expansion, which is already known to us. If x2t signal is compressed by 2, sin t by 3 signal is expanded by 3 times. Just reverse is in the case of spectrum. If signal is time compressed in frequency domain, spectrum is expansion. It is spectral expansion. Spectral expansion. If it is compressed, expanded in time domain, it's spectral compression. Just reverse. And specific case for time scaling property is if a equals to minus 1, then minus 1 upon this x of omega minus 1, which in the result of minus omega. If we replace t with minus t means inversion of the signal, then spectrum is also inversion of previous spectrum. Time scale inversion give frequency spectrum inversion also. It is a specific case of scaling. Now very important property before discussing important property of duality, just discuss some basic questions, some basic pairs. Del t equals to 1, basic Fourier transform pair. If 1 is multiplied with 1, inverse Fourier transform is 2 pi del omega. How it's come from inverse Fourier transform? I have Fourier transform is 1 upon 2 pi. This is Fourier transform of del t e power j t d omega. For inverse Fourier transform of 1 is 2 pi del omega. E power j omega naught t. Fourier transform of this term is e power minus j omega naught t. Fourier transform of this term is by adding these two terms and divided by 2, it become cos omega t, and Fourier transform of this is pi del omega minus omega naught plus del omega plus omega naught. Bracket close. By subtracting these two terms, we directly show sin omega naught t. Fourier transform of sin omega naught t is minus j pi del omega minus omega naught minus del omega plus omega naught. These are the basic Fourier transform of sine and cos which is used in communication. We can draw magnitude spectra of cos omega naught t, which shows us each monotonous frequency cos omega naught t have two spectral component, one in positive side, second one is negative side. Same frequency component with magnitude attached with these component is pi. In sine, magnitude spectra is same, but phase spectra is differ by 90 degree, minus 90 degree. This is the only basic difference between sine and cos. Magnitude spectra of sine and cos are same. Now again we discussed some properties of Fourier transform. Very important property known as duality or symmetry property. Duality or symmetry property. As per duality, if xt is Fourier transform of xt is denoted by this, then this cross this frequency domain function is replaced with t, omega is replaced with t, and this term is replaced by x of minus omega. This is known as symmetry property. Now we apply this symmetry property in different type of signal. Xt del t is 1 After applying symmetry property, we can rewrite in this way: all the component in this one replace with t, all the component of omega replace with t, and 2 pi del minus omega. This del function is even function of omega. Then we rewrite even function of omega. We took second example, signum function. We know Fourier transform of signum function is 2 upon j omega. Fourier transform of signum function is 2 upon j omega. After applying duality, we can calculate Fourier transform of 2 upon jt 2 pi signum minus omega. We cancel 2 to 2, 1 upon pi t minus j plus j signum omega, where signum is odd function of omega. So minus come out. Now 1 upon pi t Fourier transform is minus signum t. One more example, duality is useful where typical type of signal, this type of signal is available for Fourier transform. With the formula we can't calculate the Fourier transform of 1 upon pi t. So we have to use duality, and duality will provide us better approach, easy approach to solve this expression. Third case, rectangular pulse. Fourier transform of rectangular pulse is a sine omega t by 2 upon omega. We can rewrite this expression in term of sinc function sine c omega t by 2. A rect t upon t, Fourier transform is 2a sine omega t by 2 upon omega a t sinc omega t by 2. We can apply duality on this. For duality, rewrite this expression at sine c sine t upon t by 2 upon t 2 pi a rect minus omega upon capital T. If we use at sine t upon t into capital T divided by 2 upon t 2 pi a rect t, if we use omega here, because omega is even function, then minus is consumed in between, rect omega upon t. Now this function is reduced to at sine t upon t divided by 2 upon t 2 pi a rect omega upon t. It is dual of previous case. If capital T by 2 is replaced with W, then 2AW sine WT upon T two pi A rect omega upon 2W. We denote here this is the A cross W is area covered by signal. We can represent first area covered at 0 location directly mentioned from this idea. We can draw also with the help of duality. We can solve this expression also. Sine at upon pi t. We want to calculate ft of this particular function. Directly we can't Fourier transform achieve Fourier transform of sine pi t sine at upon pi t. So we have to choose duality path. At sine omega t by 2 upon omega t by 2. Use duality. A sine small t capital T by 2 small t by 2 A 2 pi rect minus omega by t. Here t by 2 is replaced with small a. A sine at upon 2 pi t by 2 A rect omega upon 2a. This signal sine at upon pi t is now Fourier transform of this is rect omega upon 2a. We can draw. Now we draw both the same pattern. Sine upon pi t rect omega upon 2a. First I draw rect. Base of the rect is height of this is 1. For drawing this function we have to make it first as a sink. A upon pi sine c at. Now I can draw. Height of this is A upon pi. Zero crossing. First zero crossing is pi by A. So with this idea I can draw both the diagram. Now we move further. I took one more example for Fourier transform. Xt is ut, unit step. We want to calculate the Fourier transform of unit step. What is idea for unit step? Unit step is composed of two signal, even plus odd component of unit step. If we segregate in term of even and odd bifurcation R, even portion is half and odd portion is signum function. We can segregate from formula also. First we graphically differentiate even and odd portion. Now we with formula ut plus u of minus t divided by 2 is half. Odd portion of ut minus u of minus t divided by 2 is signum function divided by 2. Now we took Fourier transform in both direction, half plus half signum t. Fourier transform of ut is denoted by half. Fourier transform of 1 is 2 pi del omega, and Fourier transform of signum is half 2 upon j omega. Pi del omega plus 1 upon j omega. Fourier transform of unit step.